Good morning, everyone. Before we start, a quick word on where today's material actually comes from, because I think it matters for how you should listen to it. I'm Dr. Ankur Awadia, and most of what you're about to hear over the next 3 hours is adapted directly from a textbook I authored, Fundamentals of Machine Learning. That's the cover you can see on the slide. This lecture isn't a quickly assembled set of talking points. It's a forestry and wildlife-flavored version of material that has already been written, reviewed, and published in full. So if anything I say today feels worth revisiting later, the book is where the fuller, more detailed treatment lives. We're going to talk about artificial intelligence and machine learning today, what they are, where they came from historically, and how they actually work underneath the marketing language. No coding today and no heavy mathematics. Just intuition, built up carefully, one idea at a time. By the end of this session, my real goal is that you'll be able to read an AI news story or sit through a vendor sales pitch for some new force monitoring software and actually evaluate whether the claims being made make sense, rather than simply taking them on faith. Here's the map for the next 3 hours, so you know where we're headed at every point. We'll treat artificial intelligence as the big umbrella term, the overall ambition of building machines that behave intelligently, and machine learning as one particular way of achieving that ambition, specifically by learning from examples rather than being told explicit rules. On top of machine learning sits deep learning, and on top of that, generative AI, the more recent developments that are behind tools like ChatGPT, which most of you have probably already encountered, whether in your personal life or in office work. Throughout this session, I want you to focus on intuition rather than formulas. If you walk away genuinely understanding why these systems behave the way they do, you will be far better equipped to question them sensibly than someone who has merely memorized the buzzwords. And we're going to build this entire story the way human learning itself actually develops, starting from the way I learn from everyday experience and showing, step by step, how a machine ends up doing something surprisingly similar just using numbers instead of intuition. Let's start with a question that has sat underneath this entire field for nearly a century. Can machines think? It sounds almost purely philosophical, but if you break it down, you get much more concrete and tractable questions. Can reasoning, the kind of step-by-step logical thinking we do, be mechanized, turned into a procedure that a machine can simply follow? Can learning itself be represented mathematically as numbers, weights, and equations, rather than as some mysterious inner spark? Can the human brain, a biological organ made of cells, genuinely inspire how we build computation? And perhaps the most provocative question of all, can intelligence exist without biology entirely, in silicon and electricity, rather than neurons and chemistry? We are not going to answer these definitively today. Honestly, nobody has. But keep them in the back of your mind throughout this session, because every single development we are about to discuss is, at its heart, an attempt to answer one of these 4 questions. Let's make this concrete with something everyone in this room can do without thinking twice. Can you tell which of these is a cat and which of these is a dog? Easy, right? Almost insultingly easy. Now ask yourself honestly, how did you actually decide? Did you measure anything at all? Ear length, weight, the curvature of the tail? Almost certainly not. Nobody walks around with a measuring tape for this. And here's the harder, more uncomfortable question. Could you write down the exact rule you used, in plain words, a rule that would work correctly for every single cat and every single dog you have ever seen or will ever see in the future? I suspect, if you're honest with yourself, you'll struggle to produce anything watertight. That struggle, that very specific feeling of I know it when I see it, but I can't quite explain it, is the whole point of today's lecture. Because it is exactly the struggle that gave birth to the entire field of machine learning. Why am I using cats and dogs of all the examples available to me? A few deliberate reasons. First, everyone in this room has direct, hands-on, lifelong familiarity with both animals, no specialized training required to follow along. Second, there is enormous variation within each group. A Great Dane and a Chihuahua are both unambiguously dogs, and yet they look almost nothing alike, arguably less alike than some dogs look to some cats. Third, any simple rule you try to write down for telling them apart will fail quickly, as we're about to demonstrate in painful, repetitive detail. Fourth, your own judgment about which is fuzzy and intuitive, not crisp and checklist-driven. You are not running through a mental form when you glance at an animal. And finally, this exact example extends very naturally to wildlife identification later in your careers, telling a leopard's pug mark from a tiger's, or one bird call from another in a dawn chorus. Is, cognitively speaking, the very same problem we are about to dissect using something far more familiar. So let's actually try writing the rules, the way a classical computer programmer might have approached this problem 50 or 60 years ago, before anyone seriously believed machines could learn on their own. If weight is high, perhaps it's a dog. If the ears are pointed, perhaps it's a cat. If the tail is curved, perhaps it's a dog. If the whiskers are clearly and prominently visible, perhaps it's a cat. On the face of it, taken individually, these rules look perfectly reasonable, simple, even elegant, the kind of thing you might confidently write on a whiteboard in 5 minutes. This rule-based approach was, in fact, the dominant strategy for building intelligent seeming systems for several decades of AI research, long before anyone seriously tried learning from data as an alternative. Let's now go through each of these 4 rules, one at a time, slowly, and watch every single one of them fall apart under the slightest scrutiny. Take the weight rule first, since it sounds the most objective and measurable of the bunch. A Chihuahua, unmistakably, unambiguously a dog, weighs perhaps 2 to 3 kilograms fully grown. A Maine Coon, equally unmistakably a cat, can weigh 10 to 12 kilograms, sometimes more. So if I set a threshold, say anything above 5 kilograms counts as a dog, I will misclassify both of these specific real animals, and I'll get the verdict backwards in both cases simultaneously. The deeper problem here isn't that I happen to pick the wrong number for my threshold. It's that there simply is no number anywhere on the number line that works reliably, because natural categories overlap messily in the real world. This is the first hard lesson of today's session, and I want you to really absorb it. Hard, rigid cut-offs are fragile whenever you're dealing with anything drawn from the real, messy, biological world. And in your own line of work, you will meet this exact problem constantly. There is rarely a single clean number that perfectly separates one species from another, one habitat condition from another, or one risk category from another. Try the second rule now, ears and tail shape, which feel a bit more biological, and therefore perhaps more trustworthy. Some dogs, particularly certain Spitz-type breeds like Akitas or Huskies, have very sharply pointed, erect ears. Some cats, like the Scottish Fold breed, have ears that fold forward and lie flat, the opposite of what we'd expect from a typical cat. Some dogs, like pugs, have dead straight or barely curved tails. Some cats have short, stubby, or even naturally curled tails. The Japanese bobtail is a striking example. Each of these features, examined entirely on its own, is at best an imperfect, probabilistic clue, rather than a guaranteed signal. None of them individually is reliable enough to build a confident rule around. The third rule, based on color and overall size, fails for precisely the same underlying reason as the first two. Brown is not always a dog's color. There are plenty of brown tabby cats roaming around. Black and white patterning is not always a cat's signature. Think immediately of a border collie or a Dalmatian pattern dog. Being large does not always mean dog. Some cat breeds, like the Maine Coon we mentioned earlier, are large animals. And being small does not always mean cat, toy, and teacup dog breeds exist specifically because people wanted very small dogs. Every single feature you might reach for, no matter how intuitive it feels, has exceptions the moment you look hard enough at real populations. This is the pattern I want firmly lodged in your mind going forward. Variation in the natural world defeats rigid, single-feature logic every single time without exception. And yet, here is the genuine puzzle, the thing that should make you pause. You and I recognize a cat or a dog instantly, almost effortlessly, every single time, even on individual animals we have personally never seen before in our lives. How on earth do we manage this, given everything we just demonstrated about how every individual rule fails? We are clearly not consciously running through a checklist of measurements in our heads as we glance at an animal. What we are actually doing, almost certainly, is combining a great many weak, individually unreliable clues simultaneously. The precise shape of the face, the characteristic posture, the sound it makes, the particular way it moves across a room, none of which is individually decisive on its own, but which together, combined, add up to something close to certainty. And critically, this remarkable ability is built on memory. We have each personally seen many thousands of cats and dogs over the course of our lifetimes, whether directly or in photographs and videos, and that accumulated exposure is precisely what is doing the heavy lifting. This, in a genuine nutshell, is also exactly what a machine learning model does when it works well. It simply does it with numbers and weights instead of lived intuition. Let's slow this down deliberately because this particular slide is the conceptual heart of everything that follows for the rest of today. Evidence in real-world decision-making of any kind comes in degrees. It is not a flat, binary yes or no switch. Rarely, if ever, does a single isolated clue settle or matter completely on its own. Some clues push your internal sense towards dog, some clues push you towards cat, and you are constantly, unconsciously, automatically weighing all of them against each other in something like real time. Your final judgment is the net, combined effect of all this gathered evidence taken together, not the sole verdict of any one particular feature you happen to notice first. This is what we might call fuzzy thinking, and it is something humans are remarkably, almost suspiciously good at, even though most of us could not begin to explain, in words, exactly how we do it. Now let's push this fuzzy thinking one small but crucial step further, towards something mathematical. Instead of flatly saying it's a dog or it's not a dog, what if we said, more honestly, it's 70% dog-like and 30% cat-like based on what I'm seeing? That right there is a probability. Notice it is not always pinned at 0, or 1. There is a whole rich continuum of possible values in between, and most real judgments live somewhere in that middle ground. Crucially, one single additional piece of evidence, say, you suddenly hear it meow, can shift that probability sharply, up or down, in an instant. And if you need a final, clean decision at the end of all this, you simply set a threshold, say, anything calculated above 50% gets formally called dog, anything below gets called cat. This particular idea, degrees of belief that smoothly update as new evidence arrives, combined with a threshold that finally converts accumulated belief into a hard decision, is the mathematical backbone underneath almost every machine learning system you will ever encounter in your career, however sophisticated or futuristic it might look from the outside. Uncertainty, in other words, is not some embarrassing flaw to be eliminated from a good system. It is the normal condition of the real world, and well-built systems are specifically engineered to handle that uncertainty gracefully, rather than pretending it doesn't exist. So here, finally, is the central insight of machine learning, stated as plainly as I can manage. It works on exactly the same intuition you just used, a moment ago, for telling cats from dogs, except that you doing the judging is replaced by a mathematical model running inside a computer. You give the model many examples. During a phase we call training, you also give it the correct, known answers for those examples. This one is the cat. This one is the dog. This one is the cat again. The model looks at its own mistakes as it goes and gradually adjusts its internal numbers to do a little better next time, over and over. Over many repetitions of this process, sometimes millions, it learns the underlying pattern connecting inputs to correct answers, and critically, nobody anywhere hand-wrote that pattern down as an explicit rule. It was learned entirely from the data itself. Once the model is properly trained, it can then look at a brand new image it has never once encountered and make a sensible, confident prediction about it. That is the whole idea, in its simplest possible form. Everything else we discuss for the rest of this session is detail layered on top of this one central insight. So if you remember nothing else from today, remember this slide. Before we go any further into machines specifically, let's pause for a moment on the word intelligence itself, because it gets used so loosely in everyday conversation that it helps to unpack it carefully. When researchers in this field talk seriously about intelligence, they usually mean some combination of these distinct capacities working together. Perception, taking in raw information through the senses. Memory, retaining past experience for later use. Learning, actively improving from that retained experience over time. Reasoning, drawing valid logical conclusions from available evidence. Planning, sequencing a series of actions deliberately towards some future goal. Language, communicating complex ideas using shared symbols. And judgment, weighing competing options sensibly under genuine uncertainty. No single one of these capacities, on its own, constitutes intelligence in the full sense we usually mean. It is the rich combination of several of them together that we are really after when we use the word, and as we will see repeatedly throughout today's session. Different AI systems turn out to be good at quite different subsets of this list. Some are excellent at perception but hopeless at planning, and so on. Is intelligence, in this broad sense, purely and exclusively a human trait? Clearly not, and this matters enormously for how we should think sensibly about artificial intelligence. Humans obviously learn from experience, but so, very visibly, do animals. Your own field experience in the years ahead will confirm this constantly and vividly. Whether it's an elephant calmly remembering the exact location of a water source it last visited years earlier, or a leopard quietly learning, through repeated unpleasant encounters, to avoid a particular trap or snare site. Behavior adapts to feedback across an enormous range of species, not just our own. Memory visibly shapes future action throughout the animal kingdom, from corvids hiding food to elephants navigating ancient migration routes. The honest conclusion is that intelligence comes in many different forms and many different degrees, and biological intelligence, in all its variety, long predates anything artificial that humans have ever built. This matters because it tells us that AI researchers were never inventing something entirely from nothing. Out of pure imagination, they were trying, often very imperfectly, to capture a phenomenon that nature had already independently solved many, many times over, in many strikingly different ways across the tree of life. Let's look more closely at how learning from experience actually unfolds in practice, step by step, because this exact loop is going to reappear in almost identical form when we discuss various learning algorithms. First, you observe the world around you, taking in whatever information is available. Then you try some specific action based on that observation. Sometimes that action turns out to be wrong and you make a genuine mistake. The world then gives you feedback of some kind, pleasant or unpleasant consequences that follow from what you did. And based on that feedback, you adjust your internal expectations, and your future behavior measurably improves the next time a similar situation arises. Observe, act, err. Receive feedback, improve. That compact 5-step loop is essentially universal across an enormous range of contexts. Whether we're talking about a toddler learning to walk without falling, a longur learning which fruits are safe to eat, or a piece of software gradually learning to play a strategy game at a competitive level. Now, a closely related but distinct idea: heuristics, or what we more casually and comfortably call rules of thumb in everyday conversation. These are quick mental shortcuts built up from accumulated experience, not rigorous calculations performed step by step, just practical, serviceable approximations that prove useful in ordinary daily life. If the sky looks like that particular shade of gray, it's probably going to rain within the hour. If an animal's tracks look fresh, sharply defined, and the surrounding mud is still visibly wet, it almost certainly passed through quite recently. Heuristics are explicitly not guaranteed to be correct every time. They are approximations by their very nature, but they are absolutely indispensable whenever you need to act quickly under genuine uncertainty, which, if we're honest, describes the overwhelming majority of real life, including most of the split-second field decisions you will be called upon to make in your own postings. Here's the genuine catch with heuristics, though, and it's an important one that I want you to carry with you well beyond this lecture hall. Shortcuts that reliably save time in the moment can also, quite silently and without anyone noticing, turn into bias over the longer run. They may simply ignore genuine exceptions that don't fit the usual pattern. Past experience can color present judgment in ways we don't consciously register at all. A pattern that has held true 95 times out of 100 might still mislead you quite badly on the remaining 5 exceptional cases, and frustratingly, you typically have no reliable way of knowing in advance which particular case you are currently facing, until it is already too late to course correct. This exact same problem transfers directly, almost unchanged, to machines. If a model is trained on historically biased data, it will faithfully learn and then mechanically automate that very same bias, but now operating at enormous scale, often without anyone involved necessarily noticing, until real damage has already been done. We will return to this specific danger more than once before today's session is over. Let's now shift deliberately from fuzzy, intuitive thinking towards something altogether more rigorous and formal. Can reasoning itself be properly formalized, converted into an exact, mechanically checkable structure, the way ordinary arithmetic is formal and checkable? Humans have always reasoned using arguments of various kinds, and arguments inevitably have an internal structure to them, some starting point or premise, a chain of logical inference, and a final conclusion that is meant to follow. The genuinely intriguing question, and one that turns out to be remarkably ancient: is whether at least some forms of human reasoning can be stripped entirely of their specific subject matter and reduced to pure abstract structure that could, in principle, be checked mechanically by an indifferent third party, completely regardless of what the argument happens to actually be about. This exact question is at least 23 centuries old, tracing back to Aristotle in ancient Greece, working long before anything resembling a computer existed even as a concept. Aristotle noticed, with real insight, that certain recurring patterns of reasoning are always valid, completely regardless of what specific content you happen to plug into them. His classic, oft-repeated example runs, "All humans are mortal. Socrates is a human. Therefore, Socrates is mortal." Notice carefully that the conclusion follows purely from the form of the argument, not from anything specific about Socrates personally. You could freely swap human and mortal for any other two categories that share that same logical relationship, and the underlying logic would still hold perfectly. Aristotle called these recurring patterns syllogisms, and they represent the first systematic, deliberate attempt in recorded history to cleanly separate the form of an argument from its specific content. This particular separation, form versus content, is the conceptual seed that, more than 2,000 years later, eventually grows into modern artificial intelligence. Let's look carefully at the structure of a syllogism as it appears on the screen, because this diagram is quite the direct intellectual ancestor of every single if-then rule a computer has ever executed in its entire operating history. You have a major premise, a general rule, something like all A are B. You have a minor premise, a specific concrete fact, X is A. And you combine these two together to mechanically reach a conclusion, therefore, X is B. Once you see reasoning laid out this way, as a purely abstract template using letters rather than real-world content, you can immediately see why this appealed so strongly to anyone who later wanted to mechanize thought itself. Because a machine fundamentally doesn't need to understand what A or B actually mean in the real world. It only needs to apply the structural rule correctly, mechanically, every single time. That is a profoundly important conceptual shift, and it's worth sitting with quietly for a moment before we move on. Once reasoning becomes pure structure in this way, the next conceptual step is almost inevitable, almost forced. Objects in the world become abstract symbols, and the relationships between those objects become formal rules connecting those symbols to one another. Reasoning, in this view, becomes nothing more than the correct mechanical manipulation of symbols according to fixed rules. If your starting rules happen to be correct, this kind of manipulation guarantees correct conclusions every single time. That, fundamentally, is the deep appeal of formal logic. Its absolute reliability once you trust the starting premises. But notice the catch that's already quietly lurking here, the same one we personally discovered with cats and dogs earlier this morning. Real life is messy, contradictory, and full of edge cases, and that fundamental messiness simply doesn't translate cleanly into neat symbols and tidy rules. This particular tension, clean logic on one side, messy reality on the other, is going to recur again and again throughout the entire remaining history of AI that we're about to walk through together. Roughly 2,000 years after Aristotle first identified the syllogism, an English mathematician named George Boole took this old idea of formal reasoning and turned it for the first time into genuine working mathematics. In his 1854 work, fittingly titled An Investigation of the Laws of Thought, Boole proposed treating true and false as if they were ordinary mathematical values, much like numbers, and defined precise operations, or not, that combine these values together, in exactly the same disciplined way that addition and multiplication combine ordinary numbers. This single move effectively turned logic into algebra. It might well have remained a fairly obscure mathematical curiosity for decades, except that, much later, engineers realized this exact algebra describes, with remarkable precision, how electrical switches and relay circuits actually behave when wired together. That crucial connection wasn't made by Boole himself. It took until 1937, when a young researcher named Claude Shannon, in his own master's thesis at MIT, formally showed that Boolean algebra could describe switching circuits perfectly. That is the real, slightly more nuanced reason Boolean logic is now considered, indirectly but the mathematical foundation underneath every digital computer and every microchip you have ever personally used. From your phone to your laptop. Let's ground this in something thoroughly familiar, because Boolean logic shows up constantly in everyday decisions, including a great many automated ones you already encounter daily, without necessarily noticing them as such. If it is raining and I'm about to go outside, then carry an umbrella. If an email contains certain spam-like words, or it arrives from a completely unknown sender, then flag it for review. If not formally eligible, then reject the application outright. Notice how clean, traceable, and transparent these particular rules are. You can walk back through exactly why a given decision was reached, one logical step at a time, with no mystery involved anywhere. That transparency is substantially valuable in many contexts, especially administrative ones. But also notice, and this is the catch we keep circling back to throughout today, these same rules can become brittle and uncomfortably rigid the very moment messy reality doesn't happen to fit neatly into their clean categories. Which brings us, fairly naturally, to the honest, well-documented limits of Boolean, purely rule-based logic. Real-world categories overlap constantly, as we already saw quite vividly with cats and dogs earlier today. Evidence, in practice, is frequently ambiguous or simply incomplete. Genuine uncertainty is the everyday norm in most interesting problems, not some rare exception to be quietly ignored. Exceptions to almost any rule you can write down are extremely common once you look at a large enough sample of real cases. And fuzzy problems, which frankly describe the overwhelming majority of interesting real-world problems worth solving, need learning, not just clean logic, to be handled well in practice. Keep this particular slide firmly in mind. It is the deliberate bridge connecting the logic half of AI's long history to the learning half, which we are about to spend considerable time on shortly. Long before Boole formalized any of this, though, a remarkable 17th-century German philosopher and mathematician named Gottfried Wilhelm Leibniz had already dreamed something startlingly ambitious for his time. That reasoning itself might ultimately be reduced to a pure form of calculation, no different in kind from ordinary arithmetic. He imagined a universal symbolic language, which he called Characteristica Universalis, in which genuine disputes between thoughtful people could, in principle, be settled the way you settle a straightforward arithmetic problem, by calculating a definite answer together, rather than by arguing indefinitely and getting nowhere. He referred to this proposed method as the calculus of reasoning. It went essentially nowhere practical during his own lifetime, given the technology available to him, but it is a genuinely early, remarkably clear articulation of the very same dream that quietly drives the entire field of artificial intelligence, even today. That thought itself, in some deep sense, might be computable. That precise dream gets explicitly revived in a much more concrete and technical form, almost exactly 3 centuries later, as we are about to see. A meaningful step closer to making any of this physically real came from Charles Babbage in 19th century England, who carefully designed, though notably never fully built within his own lifetime, largely due to the engineering limits and funding constraints of his era, a series of increasingly ambitious mechanical calculating engines. His central insight was that machines can perform calculation reliably, that the precise instructions guiding any given calculation can themselves be made mechanical, embodied directly in gears, cams, and levers rather than carried out laboriously by a human clerk with pen and paper. Computation, in other words, could in principle be fully automated, and hardware, the actual physical machine in front of you, matters a great deal in determining what is even possible to compute at all. Babbage's most ambitious design, the analytical engine, is widely considered today a direct conceptual ancestor of the modern general-purpose computer. Even though it was designed to run entirely on brass gears and steam power, rather than on electricity. Working closely alongside Babbage was E.T.A. Lovelace, a mathematician who made what might be the single most prescient conceptual leap in this entire historical story we're tracing. She recognized, well ahead of almost anyone else at the time, that Babbage's analytical engine wasn't fundamentally limited to merely crunching numbers, that if you represented other, quite different kinds of information numerically instead, the very same machine could manipulate absolutely anything expressible that way, including, she speculated with remarkable foresight, musical composition itself. She wrote what historians now widely recognize as the first published computer algorithm in history, a detailed method for computing a particular sequence of numbers, the Bernoulli numbers, using Babbage's still largely theoretical engine. The conceptual leap from this particular machine calculates numbers to this machine could, in principle, process any symbol whatsoever. that we choose to represent numerically is precisely the same leap that, roughly a century later, eventually makes a single piece of hardware able to run a spreadsheet 1 minute, play back a film the next, and chat with you in fluent natural language the minute after that. Now we arrive at a name nearly everyone in this room has already heard, though perhaps not in this specific historical context: Alan Turing. In the 1930s, working largely in pure mathematical logic, Turing proved something genuinely foundational for everything that followed: that a single, conceptually simple machine, following purely formal, entirely mechanical steps with no creativity or insight required, could, in principle, compute absolutely anything that is computable at all, in the fullest possible sense of that word. Crucially, that very same single machine, just given different specific instructions to follow, could perform completely different tasks without any change to its underlying hardware. This is the foundational idea of universal computation, and it is, quite directly, the precise reason your own laptop, with no hardware changes whatsoever required, can run a word processor for an hour and then a flight simulator the very next hour. Once computation is rigorously shown to be universal in exactly this sense, the once fanciful question of whether a machine could ever genuinely think stops being pure science fiction, and starts being, at the very least, a serious, well-posed scientific question worth investigating properly. In 1950, Turing tackled the deceptively simple "can machines think" question head-on, in a now famous paper published in the philosophy journal Mind, but he made a clever strategic move in how he approached it. Rather than getting hopelessly tangled up in vague, essentially unanswerable philosophical definitions of what thinking truly means at some deep metaphysical level, he proposed judging machines purely and exclusively by their observable external behavior. Could a machine side of a written conversation be reliably indistinguishable from a human side, as judged by an attentive human evaluator? This clever move sidesteps the unanswerable metaphysical question entirely and replaces it with something genuinely testable in practice. Turing called this proposed test the imitation game, though it is now far better known almost universally as the Turing test. Notice that this exact question hasn't gone away in the intervening 75 years at all. Every single time someone today argues passionately about whether ChatGPT is really intelligent in some deep sense, they are, almost word for word, simply rerunning Turing's original decades-old debate, often without realizing it. Let's pause for a moment and carefully retrace the entire historical path we've just walked together, because it really is an elegant intellectual chain when you see it laid out in sequence like this. Formal reasoning itself began with Aristotle's careful study of logic. That logic became rigorous mathematics in George Boole's capable hands 2,000 years later. That mathematics became actual physical computation through Alan Turing's foundational theoretical work. That computation, in turn, became something programmable, general purpose, and runnable on real, physical hardware sitting on a desk. And artificial intelligence, as a coherent field of study, is fundamentally the open question of whether, and precisely how, intelligence itself can be computed, using exactly this long chain of conceptual tools we've just traced together. Every individual step in this chain took multiple centuries to develop properly. The entire field of AI, as we're about to see in the very next slide, took only a single summer to be officially and formally named. That defining summer happened in 1956 at Dartmouth College in rural New Hampshire, in the United States. A fairly small group of researchers, including John McCarthy, who organized the whole gathering and would go on to coin the field's name, Marvin Minsky, then at Harvard, Nathaniel Rochester, an engineer from IBM, and Claude Shannon himself, the same Shannon who had earlier connected Boole's algebra to switching circuits, gathered for what was, on paper, a fairly modest low-key summer workshop. But the working agenda they proposed was anything but modest in its ambition. They suggested, in writing, that essentially every conceivable aspect of learning, and indeed every other distinctive feature of intelligence, could in principle be described with such mathematical precision that a machine could be built to simulate it faithfully. Out of this single summer meeting, the field formally acquired its lasting name, artificial intelligence, along with an enormous, almost giddy wave of professional optimism. Researchers at the time sincerely believed that machine intelligence, broadly comparable to a human's, was perhaps just 1 or 2 decades away at most. They were spectacularly wrong about that particular timeline, as we are about to see in some detail. But the name itself and the underlying ambition behind it stuck around permanently right up to today. The earliest serious, well-funded attempts at building AI, following directly from this Dartmouth-fueled optimism, leaned very heavily on logic and explicit rules. The symbolic tradition we have been carefully building up to over the last several slides. The basic approach was to represent knowledge explicitly as symbols, write careful rules to reason systematically over those symbols, and search methodically through the entire space of possible solutions to a given problem. This worked remarkably well, in tightly constrained, well-defined artificial worlds, playing chess competently, solving formal logic puzzles, even proving certain mathematical theorems automatically. But the moment these early systems were exposed to the genuine, unfiltered messiness of the real world outside the laboratory, vague natural language, incomplete or contradictory information, endless small exceptions, they struggled badly, often embarrassingly so. This is precisely the same brittleness we personally discovered earlier today, with our simple cat and dog rules, just now playing out at a vastly larger, more expensive, and more consequential scale across an entire emerging research field. One major, practical product to emerge from this symbolic rule-based era was the expert system, software specifically designed to capture and encode the detailed knowledge of a particular human expert, as a large, carefully assembled collection of if-then rules. Medical diagnosis systems for specific diseases, geological prospecting tools for mineral exploration, even early systems advising loan officers on which applications to approve, were all built using essentially this same approach. The resulting decisions were genuinely transparent. You could always trace, with complete confidence, exactly which specific rule had fired and precisely why, all the way down to the underlying logic. And these systems performed well, often impressively so, within narrow, carefully bounded, well-defined domains where the relevant knowledge was relatively stable. But maintaining and continuously updating these large rule sets as underlying knowledge or circumstances inevitably changed over time turned out, in practice, to be enormously labor-intensive. And that ongoing maintenance burden is ultimately what limited how far this entire approach could realistically scale. So why, in the end, did rule-based AI become so brittle that it eventually fell out of favor as the dominant approach in the field? Because rules fundamentally need to anticipate every possible exception in advance, and real life simply keeps generating new, unanticipated exceptions faster than anyone can write rules to handle them. Encoding genuine uncertainty into rigid if-then logic structures is, at best, deeply awkward and unnatural. Common sense, the vast, largely unstated background knowledge that humans rely on constantly without even noticing, turned out to be extraordinarily difficult to write down explicitly, no matter how many rules researchers patiently added. And the sheer ongoing maintenance cost of an ever-growing, ever more tangled rulebook eventually became practically unsustainable for any reasonably complex domain. This is, once again, exactly the same lesson we personally learned from cats and dogs at the very start of today's session, just now playing out at the scale of an entire international research field across several decades of sustained, well-funded effort. While the rule-based symbolic camp of researchers was running headlong into these particular walls, a completely different group working largely in parallel was asking a fundamentally different kind of question altogether. Instead of laboriously writing down explicit rules for intelligent-looking behavior, what if researchers instead tried to copy, even very crudely, the underlying physical structure that actually produces intelligence in living creatures in the first place, namely the brain itself? Could individual neurons be modeled mathematically, even in drastically simplified form? Could genuine learning emerge naturally from large networks of very simple, densely connected units, rather than being explicitly programmed in by a human engineer line by line? This alternative philosophy, deliberately using the biological brain purely as loose inspiration, not as any kind of literal, faithful blueprint to be copied exactly, is called connectionism. And it is the direct intellectual ancestor of every neural network and every large language model you will hear discussed for the remainder of today's session. The connectionist story properly begins in 1943 with two researchers, Warren McCulloch, a neurophysiologist, and Walter Pitts, a logician, who together proposed the very first mathematical model of a single neuron. Look carefully at the diagram on the screen. Several separate inputs arrive at the unit, each one multiplied by a corresponding weight that reflects its relative importance. They get summed together into one combined value. And if that sum value happens to cross a certain fixed threshold, the unit fires and produces an output. Otherwise, it simply stays silent, unproduces nothing. It is, admittedly, a drastically oversimplified caricature of how a real, messy biological neuron actually behaves chemically and electrically. But it was revolutionary at the time because it showed, for the very first time in history, that something as deeply biological as a neuron could be captured precisely, completely, and faithfully in pure mathematics. Every neural network built since that 1943 paper, including, quite literally, the enormous ones running inside the chatbots many of you have probably already used on your own phones, is, at its mathematical core, simply a vast number of these same simple units, wired together in elaborate patterns. 6 years later, in 1949, Donald Hebb, a psychologist working at McGill University, added the missing piece to this emerging picture. How does learning actually happen, mechanically, within a network of connected neurons in the first place? Hebb proposed, based on careful reasoning about neural anatomy, that connections between two neurons strengthen specifically when those two neurons are repeatedly active together at roughly the same time. A principle informally remembered today, decades later, through the Keiichi shorthand cells that fire together, wire together, even though Hebb himself never actually used that exact memorable phrase in his own writing. Learning, in this particular view, isn't some separate, mysterious, almost magical process happening elsewhere in the brain. It is simply the gradual, mechanical reweighting of existing connections based directly on accumulated experience over time. This single, elegant idea that lived experience leaves a genuine physical trace by quietly altering connection strengths inside a network underlies the entire training process of essentially every neural network in active use today, including, again, the very large ones we'll be discussing in detail later this session. These two foundational ideas, McCulloch and Pitts's mathematical model of a single neuron, and Hebb's proposed rule for how learning actually happens between neurons, came together explicitly in 1958 in Frank Rosenblatt's perceptron, built at the Cornell Aeronautical Laboratory, with funding from the U.S. Office of Naval Research, and widely regarded today as the first genuine learning machine ever constructed. A perceptron receives several separate inputs, assigns its own adjustable weight to each one, combines them all together, and produces a single output based on that combination. Critically, and this is the new part, when it makes a mistake on a given example, it automatically adjusts its own internal weights afterward to do better next time. It learns directly from its own errors, entirely automatically, with no human anywhere rewriting any explicit rule by hand in between attempts. This was, at the time, an absolutely enormous moment in the field. The New York Times, reporting on a Navy press conference about the device, speculated in print that machines, capable of walking, talking, seeing, writing, and even reproducing themselves, were just around the corner, perhaps within a single human generation. The reality, as we are about to see quite clearly in the very next slide, turned out to be considerably more modest than that breathless newspaper prediction. What could this original perceptron actually learn to do, in concrete practical terms? It could reliably separate fairly simple patterns into two distinct categories, and it learned a dividing boundary between them entirely from worked examples, with absolutely no rule handwritten in advance by any programmer. This worked beautifully, almost perfectly, whenever the two categories in question happened to be what mathematicians call linearly separable, meaning you could, in principle, draw a single straight line, or in higher dimensions a single flat plane that cleanly and completely divides the two groups from each other with zero errors. This was genuine, rigorously demonstrated proof that machine learning of a sort was, in fact, possible, not merely a theoretical fantasy. But, and this particular but is genuinely important, so please note it carefully, the perceptron had hard, mathematically provable limits. And discovering exactly where those specific limits sat would very shortly trigger the entire field's first serious career-altering crisis. That crisis arrived in 1969 in a rigorous, carefully argued, and ultimately highly influential book written by Marvin Minsky and Seymour Papert, who proved with mathematical certainty that simple, single-layer perceptrons could not solve certain basic problems. The diagram currently on screen shows the classic textbook example, known as the XOR problem. Look carefully. The data points belonging to class 1 inches and class 0 inches are deliberately arranged so that absolutely no single straight line, drawn anywhere on this plane, can cleanly separate the two classes from each other. The required category boundary needs a curve or alternatively multiple stacked layers working together. And a single layer perceptron simply has no mathematical way whatsoever to produce either of those things on its own. Combined with the weak computing hardware available at the time and wildly inflated public expectations stirred up by enthusiastic press coverage, this one book caused funding and serious research interest in neural networks to collapse almost overnight across the field. Neural network-based AI essentially went dormant for well over a decade as a result, a sobering, still relevant reminder of how a single, precisely targeted, well-proven limitation can stall an entire promising research direction for years, even when the underlying idea is fundamentally sound, as history would eventually show. Stepping back from the historical detail for a moment, we now have two distinct philosophies of AI clearly laid out on the table in front of us, and it's worth naming both of them clearly before we move on. Symbolic AI represents knowledge as explicit rules and formal logic, the entire Aristotle through expert systems lineage we've just walked through in careful detail. Connectionist AI represents knowledge implicitly instead, encoded in networks of weighted connections that gradually adapt through learning, the McCulloch-Pitts through perceptron lineage we covered immediately afterward. One tradition is explicit, transparent, and rule-driven. The other is adaptive, opaque, and experience-driven. For several decades, these two approaches were treated by their respective practitioners as rival camps, almost ideologically opposed to one another at academic conferences. As we will see clearly by the end of today's session, modern AI does not ultimately pick a single winner between these two traditions. It borrows pragmatically and freely from both, often within the very same deployed system, sometimes even within the very same trained model. Let's be properly fair to symbolic AI here and list its genuine, well-documented strengths because it's tempting, with the comfortable benefit of hindsight, to dismiss it too quickly and too completely as old-fashioned. Its underlying reasoning is transparent. You can always trace, step by step, exactly why any particular conclusion was reached. It is correspondingly easy to inspect, formally audit, and clearly explain to a non-technical stakeholder, which matters enormously in regulated or legal contexts. It is excellent for formal, precisely well-defined rules where the domain knowledge is stable. It was, and in many specialized contexts still remains, useful for expert systems operating within narrow domains. And it continues to work very well precisely in those well-defined domains where the relevant rules are known, stable, and unlikely to change suddenly. Now, equally fairly, the honest weaknesses of symbolic AI, the specific weaknesses that ultimately limited just how far this whole approach could scale in the real world. It is brittle the very moment unanticipated exceptions appear, which, as we have firmly established by now, is most of the time once you leave a tightly controlled laboratory setting. Encoding genuine common sense into a set of explicit rules turns out to be extraordinarily, almost comically difficult in practice. It performs quite poorly when confronted with messy, noisy, real-world data of the kind you'll actually encounter in the field. Rule sets, left unchecked, tend to multiply almost uncontrollably as engineers try to patch every newly discovered edge case, one at a time. And it is fundamentally, structurally weak at perception-style tasks, specifically recognizing images, understanding spoken speech, precisely the tasks that come effortlessly, almost for free, to biological brains shaped by millions of years of evolution. Connectionist AI's strengths are, fairly neatly, almost a mirror image of symbolic AI's documented weaknesses, which is exactly why these two traditions eventually became complementary, rather than remaining purely rival approaches forever. It learns directly and automatically from worked examples, with no explicit rules needing to be handwritten by an engineer. It handles noisy, imperfect, real-world data gracefully, without breaking down at the first unexpected input. It is genuinely, demonstrably good at perception-heavy tasks specifically, images and speech most of all, but increasingly text and language too. It adapts smoothly through ongoing training rather than needing to be painstakingly reprogrammed by hand every time circumstances shift. And it can discover hidden, non-obvious patterns buried within data that no individual human analyst had previously noticed or thought to explicitly articulate. But Connectionist AI carries its own very real, well-documented costs, and they are worth being completely honest about here. Because you will meet every single one of them constantly in today's public discourse around modern AI systems. It needs substantial, often very large, amounts of training data to learn anything reliably useful. It needs substantial computing power, often running for days or weeks on specialized hardware, simply to train in the first place. It can become a genuine black box, where even its own original creators cannot always fully explain why it produced one specific decision rather than another plausible-sounding alternative. It may inadvertently learn and then mechanically amplify at scale. Whatever bias happens to be quietly lurking in its training data. And it can fail in unpredictable, sometimes bizarre and almost comical ways on inputs it has not properly learned to handle, with no obvious warning sign beforehand. Please keep this particular list of 5 points firmly in mind as we proceed. We will return to every single one of them, in considerably more depth and with concrete real-world examples, during the second half of today's session. Putting both strands of this history together, the broader history of AI from roughly the mid-1970s through the late 1980s is often described quite vividly as a series of AI winters. The first domino fell in 1966 with a U.S. government report from the Automatic Language Processing Advisory Committee, commonly known as the ALPAC report, which concluded, after the American government had already spent roughly $20 million chasing automated machine translation, that the resulting systems were nowhere near practical and showed little prospect of catching up to human translators anytime soon. Funding for that entire direction was essentially eliminated overnight. Then, in 1973, the British government commissioned Sir James Lighthill, a respected applied mathematician deliberately chosen because he was a complete outsider to the field, to independently evaluate UK research. His Lighthill report bluntly concluded that AI had failed to meet its own grandiose objectives. Specifically citing a problem he termed a combinatorial explosion, where the number of possibilities a system needs to consider grows so explosively fast that no computer of that era could keep up. UK university funding for AI was cut dramatically and almost immediately as a result. High expectations had been set repeatedly by enthusiastic researchers themselves. Computing hardware remained limited throughout this period, and available training data was scarce by any modern standard. Promised breakthroughs simply failed to materialize on the confident timelines that had been sold to funders. And predictably, funding agencies and the wider public both lost patience and pulled back their investment quite sharply. The term AI winter itself was only coined later, in 1984, by researchers Roger Schenck and Marvin Minsky during a public debate at an AI conference, deliberately echoing the then topical idea of a nuclear winter to warn colleagues that excessive hype could trigger an equally severe funding collapse. This boom and bust cycle of inflated promises, followed by genuine disappointment, is worth remembering today, because, as we will discuss again towards the end of this session, some argue we may currently be living through an echo of exactly the same pattern. So what actually changed concretely to bring AI roaring back from that long, painful winter into the dominant, ubiquitous technology it represents today? 3 distinct ingredients converged more or less simultaneously from roughly the 2000s onward, each reinforcing the others. Internet-scale data became freely available for the first time in human history, billions upon billions of images, documents, and recorded interactions, accessible to researchers in a way that was simply unimaginable even one generation earlier. Powerful, relatively affordable GPUs, graphics processing units, originally designed purely for rendering video game graphics smoothly, turned out, almost by happy accident, to be extraordinarily well suited to exactly the kind of repetitive parallel mathematics that neural networks fundamentally required to train. Better, more efficient training algorithms were developed steadily by researchers across multiple institutions. Open-source software tools dramatically lowered the practical barrier to entry for ordinary researchers and hobbyists working anywhere in the world. And serious, sustained commercial investment from major technology companies with deep pockets poured into the field once practical, demonstrable results finally started appearing reliably. Let's look at each of these 3 core ingredients, data, compute, and algorithms, a little more closely, one at a time, over the next few slides. Data is, quite literally, the fuel that powers any learning system from the ground up. Without a sufficient supply of good representative examples, there is simply nothing meaningful for the model to learn from, no matter how clever the underlying algorithm might be. The decisive shift towards large datasets occurring through the 2000s and into the 2010s fundamentally changed what was practically achievable almost overnight. But, and this is a point I want to stress because you will encounter it constantly in your own future work, quality matters every bit as much as sheer quantity, arguably more so. Bad, biased, or simply unrepresentative data reliably produces bad, biased models, no matter how enormous that underlying dataset happens to be in raw size. And the very act of collecting data at this kind of massive scale itself raises real, substantive ethical questions around privacy, informed consent, and basic fairness that we will touch on again a little later in this session. The second essential ingredient is raw computing hardware itself. Training any modern model requires an absolutely enormous number of individual mathematical calculations performed over and over, layer after layer, for every single training example. GPUs happen to be extremely good by their fundamental design at performing many such calculations simultaneously in genuine parallel, rather than working through them one tedious step after another the way an ordinary processor does. This parallel processing capability is precisely why training a large modern model can realistically be done in mere weeks, rather than requiring centuries of sequential computation on older hardware. Training remains substantially expensive even today, both in raw money and in electricity consumed. And the overall demand for ever more computing power continues to rise sharply year on year as models keep growing larger and more capable. The third essential ingredient is better algorithms, smarter, more efficient mathematical procedures, governing precisely how a model actually learns from its own mistakes during training. Over several decades of patient research, scientists have steadily developed techniques that learn more efficiently from limited data, generalize noticeably better to new unseen situations, and scale gracefully to enormous datasets without breaking down. None of the abundant available data and none of the powerful available hardware would ultimately matter very much without algorithms clever enough to actually exploit both of them effectively. It is specifically the combination of all three ingredients, working together, data, compute, and algorithms simultaneously, and not any single one of them in isolation, that makes today's AI practical and broadly usable in ways it simply was not, even as recently as 15 years ago. Now that we have the full historical picture properly in place, let's carefully nail down some essential terminology. Because these four particular terms get thrown around quite loosely in popular media, often used interchangeably by journalists in ways that cause confusion. Artificial intelligence is the broad field overall, the entire ambition we've been discussing all morning. Machine learning is one particular approach within that broader field, specifically learning useful patterns from data, rather than following handwritten rules. Deep learning is, in turn, one particular approach within machine learning, specifically using many layered neural networks of the kind we discussed a few slides ago. And generative AI is a modern, highly visible application that has emerged largely from deep learning, systems specifically built to create entirely new content, rather than simply classifying or predicting based on existing content. These four terms overlap substantially with one another in practice, but they are absolutely not identical, and using them with proper precision will make you sound, and more importantly, actually think, considerably more clearly than the great majority of people currently writing breathlessly about this topic in the popular press. Let's take each of these four terms in turn now, starting with the broadest one on our list. Artificial intelligence, defined broadly and properly, is any system at all that performs tasks we conventionally associate with intelligence, perceiving the world, understanding natural language, reasoning logically, planning ahead, exercising practical judgment under uncertainty. Critically, such a system may achieve all of this through purely handwritten rules, through learning patterns from data, or through some thoughtful combination of both approaches working together. Recall that both the symbolic and connectedness traditions we covered in detail earlier both count as legitimate forms of AI, despite their very different methods. So artificial intelligence is, by clear definition, a considerably broader category than machine learning. Every machine learning system is, by definition, a form of AI. But not every AI system actually uses machine learning at all. That classical rule-based expert system from the 1980s we discussed earlier was genuine, working AI. even though there was no learning from data involved anywhere in its design. Machine learning, by clear contrast, has a much narrower and considerably more specific definition. It is, specifically and precisely, the particular method of learning patterns from data, rather than from explicit, handwritten rules supplied by a programmer. The rules that a machine learning system ultimately ends up following are not written down by a human programmer one line at a time. They emerge organically from the training process itself. And the system's predictions measurably improve as it is progressively exposed to more relevant data over time. This particular approach proves especially useful precisely in exactly those situations where handwritten rules, as we demonstrated quite thoroughly with cats and dogs at the very start of this session, simply and predictably fail. Deep learning is a specific and currently extremely prominent subset of machine learning. It uses neural networks containing many layers stacked one after another in sequence, hence the descriptive word deep in its name. Crucially, these deep networks learn useful internal representations of the underlying data entirely automatically, without requiring a human engineer to manually decide in advance which specific features actually matter for the task at hand. This particular property makes deep learning especially strong for images, speech, and natural language, specifically exactly the perceptual, pattern-rich tasks where symbolic AI historically struggled the very most. As we discussed earlier, the unavoidable trade-off is that deep learning typically demands substantially more training data and considerably more computing power, and the resulting trained models tend to be noticeably less explainable, less transparent, than simpler, more traditional statistical approaches. Generative AI, finally, refers specifically to systems deliberately built to create new content of some kind, rather than simply classifying a given input into a category or predicting a single number from it. This newly created content can take the form of written text, generated images, synthesized audio, or even functioning computer code. These systems learn the underlying statistical patterns present in enormous training datasets, and then generate entirely fresh outputs that faithfully follow those same learned statistical patterns without ever literally copying any single training example outright. This proves useful for drafting documents quickly, summarizing lengthy material efficiently, and synthesizing new ideas out of existing source material. But I want you to remember this particular final point, especially clearly because it sets up our extended discussion of hallucination a little later today. A generative system can produce extremely plausible sounding, perfectly fluent output that is nonetheless entirely and confidently false. Let's now zoom in carefully on the actual underlying mechanics, contrasting classical programming directly against machine learning, placed side by side for direct comparison. In classical programming, a human programmer writes out explicit, complete rules in advance, and the computer then faithfully, mechanically follows those exact instructions, one step at a time, with no deviation. This particular approach works very well indeed for clearly defined tasks where the relevant rules are fully known in advance by the programmer. But every single relevant exception must be carefully anticipated by that human programmer well ahead of time. And every newly discovered exception that emerges later requires writing yet another additional patch rule, specifically to handle at exactly the same brittleness problem we already identified earlier today, with our simple cat and dog rules. Machine learning fundamentally reverses this entire flow of information, and I would like you to sit with this particular reversal for a moment, because it is the single most important conceptual shift in the whole of today's 3-hour session. Instead of carefully providing rules up front, you simply provide worked examples. Instead of laboriously writing a program line by line, you also separately provide the known, correct answers for those specific examples. The model then learns the hidden pattern connecting examples to answers entirely on its own, through repeated exposure and adjustment. Once properly trained, when new data eventually arrives that the model has never seen before, the model produces a fresh prediction based purely on the underlying pattern it independently learned during training. Learning, in short, has fully replaced rule writing as the core operating mechanism. This is the single sentence I would most like every one of you to remember clearly from the entire first 90 minutes of today's session, even if every other detail eventually fades from memory. Why does any of this actually matter concretely for your own future work, beyond being an interesting intellectual story? Because real-world categories you will deal with constantly, whether you're working with forest types, individual animal species, encroachment risk levels, or fire susceptibility ratings, are almost always fuzzy in exactly the same way cats and dogs turned out to be fuzzy this morning. Rule-based systems, when applied to such inherently fuzzy categories, reliably generate an endless, unmanageable stream of awkward exceptions over time. Data, on the other hand, can reveal underlying patterns that no individual human expert ever sat down and explicitly wrote out as a formal rule. Models built carefully on good data can adapt sensibly as underlying conditions gradually change over the years. But, and this caveat is essential, not merely a polite formality, any such model absolutely must be properly, rigorously tested before you trust it. A theme we will return to in considerable practical detail very shortly. There is an important missing piece in the story so far, an entire academic discipline that quietly underlies almost everything we have discussed up to this point: statistics. Data, by its very nature, inherently contains variation and a certain amount of irreducible noise. No two measurements taken in the real world are ever perfectly, exactly identical, even of the supposedly same quantity. Statistics is the formal academic discipline specifically built to study exactly this kind of inherent uncertainty and variation in a rigorous way. Statistical models capture meaningful relationships between different variables present in data. And making any useful prediction always requires generalizing sensibly beyond the exact specific examples you personally happen to observe and record. Modern machine learning, properly understood, is built quite directly on top of more than a full century of prior statistical theory. It most certainly did not spring into existence fully formed from nothing, despite how it's sometimes breathlessly portrayed in popular technology journalism. Let's briefly recap the entire historical journey we've covered so far, because we are about to deliberately leave history behind for a while and move squarely into the practical, hands-on mechanics of how machine learning actually operates day to day. Formal logic, starting with Aristotle, gave humanity its first rigorous rules for valid reasoning. Computers, descending directly from Babbage's mechanical designs and Turing's theoretical breakthroughs, eventually made those abstract rules mechanically, electronically executable at speed. Brain-inspired connectedness models, in turn, suggested a compelling alternative path. That learning itself, rather than painstaking rule writing by hand, might generate intelligent-looking behavior, all on its own. And the fortunate, near-simultaneous convergence of abundant data, powerful compute, and increasingly clever algorithms eventually revived this connectedness idea, decades after it had been largely written off as a dead end, transforming it into the single dominant force in today's AI landscape worldwide. So, in entirely concrete and practical terms now, how do machines actually learn mechanically day to day? Data enters the system from some source. A model learns a useful pattern, connecting that incoming data to known, correct outcomes supplied during training. Its resulting predictions are then rigorously tested against entirely new, previously unseen cases it has never encountered before. Different specific algorithms accomplish this core learning step in different mathematical ways, as we are about to see very shortly, when we tour several of the most important ones together. And modern, more advanced forms of AI, including the large language models everyone is talking about right now, simply extend these exact same basic underlying ideas, applying them at a far larger scale to far more complex and varied kinds of data, including natural human language itself. Let's now formalize the practical workflow that is followed in essentially every serious real-world machine learning project, what practitioners commonly call the machine learning pipeline. First, you collect relevant data from whatever sources are available to you. Second, you carefully prepare and clean that raw data, a step that, in practice, usually consumes the clear majority of any real project's total time and effort, far more than the modeling itself. Third, you choose an appropriate type of model specifically suited to your particular problem. Fourth, you train that chosen model carefully on your prepared data. Fifth, you rigorously, honestly evaluate exactly how well it actually performs on data it hasn't seen. And finally, you deploy it into genuine, real-world use and continue actively monitoring its ongoing performance over time. Since real-world conditions inevitably shift and drift away from whatever the training data originally captured, we are going to walk through several of these individual stages in somewhat more depth over the next several slides, one at a time. Let's start with the very first stage in that pipeline. Data itself, the genuine raw material that every single model is ultimately built from, with no exceptions. Data can take many strikingly different forms in practice: written text documents, still images, and moving video, neatly structured numbers arranged in tables, recorded audio, and speech, continuous sensor readings of various kinds, and detailed records of user or animal behavior over time. In your own specific line of work, this might concretely mean satellite imagery of forest cover, camera trap photographs triggered by passing wildlife, careful forest inventory measurements taken by survey teams, or rainfall and temperature sensor logs collected automatically over months or years. Whatever specific form the data happens to take in your case, this is the genuine starting point of any machine learning project worth doing, without sufficiently representative, sufficiently abundant data. None of the later, more glamorous-sounding stages have anything meaningful whatsoever to actually work with. From this raw data, a model extracts what are technically called features, the specific input clues it actually pays close attention to when forming a prediction. In an ordinary spreadsheet of numbers, features are typically just individual columns, say, rainfall measured in millimeters, elevation above sea level, or measured canopy density as a percentage. In a digital image, features might effectively be individual pixel values or, more usefully, recurring patterns detected across meaningful groups of nearby pixels. Good, informative features make the entire learning process dramatically easier for any model to succeed at. Poor, irrelevant, or redundant features, on the other hand, will sharply and permanently limit how well any model can possibly perform on the task, no matter how mathematically sophisticated the underlying learning algorithm happens to be. Alongside features sit labels, the known, independently verified correct answers that a model is actually trained against during the learning process. Cat or dog is a label. Spam or not spam is a label. In a forestry context, specifically, degraded or healthy canopy condition, or a precise species name attached to a specimen, would equally and naturally count as a label. During training, the model continuously compares its own tentative prediction against this known, trusted label, and the resulting gap, or error, between prediction and ground truth is precisely what drives and guides the entire learning process forward, step by step, example by example. So how does the actual training process unfold, mechanically, step by careful step, once you have both features and labels ready? The model looks closely at a single training example and produces its own tentative prediction for it. It then compares that prediction directly against the known, correct label supplied for that example. Based on the size and direction of any resulting error, it adjusts its own internal settings slightly, the very same weights we first discussed back on the perceptron slide earlier today, specifically to reduce that particular error somewhat for next time. And then the entire process simply repeats over and over, often many thousands or even many millions of times across the full training dataset, gradually and patiently refining the model with each successive pass through the available data. It is frankly a slow, iterative, almost grinding process, much less like a sudden flash of dramatic understanding arriving all at once, and much more like patient, repetitive practice building up gradually over time, not unlike a musician practicing scales. Here's a question that trips up almost everyone the very first time they encounter machine learning seriously. How do we actually know, with any confidence, whether a model has genuinely learned something useful and generalizable, rather than simply having memorized its specific training examples by rote? The honest answer is testing, specifically evaluating the trained model on a separate set of examples it has never once seen during the entire training process. This reveals genuine, honest, real-world performance, rather than performance that's artificially and misleadingly inflated, purely by familiarity with the exact training data it already memorized. It reliably detects pure memorization whenever it has quietly occurred. It properly, honestly measures genuine generalization ability, rather than mere recall. And perhaps most importantly of all, from a practical standpoint, it protects you, the working practitioner, from a very human and surprisingly tempting form of self-deception, mistaking a model that has simply memorized its own homework for one that has understood the underlying material well enough to handle something new. This naturally brings us directly to generalization, which is the ultimate goal of the entire training process from start to finish, not raw training accuracy for its own sake, however impressive that number might look in a report. High accuracy measured purely on the original training data is simply not sufficient evidence on its own, however good it looks. What truly matters in the end is how the model performs on entirely new cases it has never previously encountered in any form. It absolutely must handle the natural variation present in real-world data gracefully, rather than narrowly memorizing only the specific examples it happened to be shown during a finite training phase. A model that merely memorizes has, in any meaningful practical sense, learned essentially nothing of genuine, lasting value going forward. Generalization, performing reliably well on the unfamiliar, is the actual working definition of true machine learning success. The single most common failure mode that directly violates this principle of generalization is called overfitting, and the diagram currently on this slide makes the underlying danger vivid and concrete. On the left side, you see a sensible, reasonably smooth boundary separating the two color-coded classes. It achieves 97% accuracy on its own training data, and still a respectable 94% accuracy on new, previously unseen data, a small and entirely acceptable drop. On the right side, an overly complex, wildly wiggling boundary achieves a near perfect 99% accuracy on its training data, but then collapses badly, all the way down to just 63% on that same new unseen data. That particular model on the right has effectively memorized the specific noise and random quirks of its own training examples, rather than learning the deeper underlying pattern connecting the two classes together. Too much model complexity, somewhat paradoxically, can actively hurt real-world performance rather than helping it. And a separate validation step deliberately testing on data held back specifically during training and never used to fit the model is precisely how careful practitioners catch this exact problem before it ever causes real, costly damage once the model is actually deployed in the field. Given everything we've just carefully covered about overfitting and generalization, why do so many different machine learning algorithms exist at all, rather than the field simply settling on one single best algorithm for everyone to use? Because there is no single best algorithm for every conceivable problem you might face. That is, in fact, a formal, rigorously provable mathematical result within the field itself. Different kinds of data and different kinds of underlying problems benefit from fundamentally different specific tools, much as a forester reaches for different instruments depending on whether they're measuring girth, height, or a canopy cover. Some algorithms deliberately prioritize being highly explainable and fully transparent to a human reviewer. Others deliberately prioritize being maximally flexible and accurate, sometimes accepting a real cost in transparency as the price of that extra accuracy. Your own specific choice of algorithm, in practice, should always depend carefully on your specific purpose at hand. Let's now actually tour the major families of these algorithms together, one at a time, so you walk away with genuine working intuition for each. The simplest and historically by far the oldest of all these algorithms is linear regression, with roots going back several centuries to the works of Newton, Gauss, Legendre, and Galton. It is used specifically whenever your desired output is a continuous number, predicting an exact rainfall amount or a specific tree height or a population count, rather than predicting which discrete category something belongs to. It finds the underlying relationship between your input variables and that output by literally, mathematically fitting the single best-fitting straight line through your scattered data points, in a way that carefully minimizes the overall prediction error summed across every single one of them. It is simple, and importantly and valuably, it is highly interpretable. You can directly read off from the fitted equation itself exactly how much the output is expected to change for each one unit change in a given input variable. This particular interpretability is precisely why linear regression remains widely popular today in serious applied work, despite being well over 2 centuries old as a mathematical technique, far older than anything else we'll discuss today. Sometimes, though, the underlying relationship hiding in your data isn't a straight line at all. It visibly curves, bends, or even reverses direction partway through the range of your data. Polynomial regression handles this situation by deliberately adding curved polynomial mathematical terms that allow the fitted line itself to bend and flex, following that observed curvature far more faithfully than a straight line ever could. This makes the resulting model considerably more flexible than plain, ordinary linear regression. But, and you should already be anticipating this particular caveat, given our earlier extended discussion of overfitting a few slides back, too much added flexibility, achieved simply by throwing in too many high-order polynomial terms, can very easily tip over into serious overfitting. Useful in the right circumstances, but it does demand real, deliberate caution in exactly how it's applied in practice. Logistic regression, despite its somewhat confusing and historically misleading name, is actually used specifically for predicting categories, not continuous numbers at all. Predicting, say, encroachment detected versus no encroachment detected, rather than predicting some precise underlying quantity. It predicts a clean probability value somewhere between 0 and 1, and you then apply a chosen threshold to convert that calculated probability into a final, concrete class decision. Exactly the same probability and threshold idea we deliberately introduced all the way back with our original cats and dogs example this morning. It remains simple and properly interpretable in its own right, and for that specific reason, it serves today as an extremely common baseline model that careful practitioners routinely compare every fancier, more complex algorithm against before deciding the extra complexity is actually justified by better real performance. K-nearest neighbors takes an entirely different and very intuitive approach to the same basic problem. To classify any brand new case, it simply compares that new case directly against a stored library of old, previously seen cases, finds the small handful that are most similar to it. Its so-called nearest neighbors in some sensible measure of distance, and then lets those nearby neighbors effectively vote on the correct answer for the new case. There is no underlying equation being fitted at all here, no curve and no boundary calculated in advance. It works purely and directly by similarity, which is precisely why it feels so immediately intuitive and is so easy to explain clearly to a non-technical audience without any mathematics at all. The main genuine catch is that it can be quite sensitive to exactly how you choose to measure distance or similarity between cases, and to the particular numerical scale of your different input variables, which need careful handling before the method works well. Support vector machines take yet another mathematically quite different approach, one specifically built in, optimized for classification problems. Rather than letting neighbors informally vote, an SVM finds the single best boundary that separates two classes, specifically by maximizing the margin, the empty buffer space, between that chosen boundary and the very nearest data points belonging to each of the two classes. Look carefully at the diagram on screen. This is genuine real-world data, the flipper length and bill depth of measurements of two distinct penguin species, Adelie and Gentoo, originally collected by researchers studying the Palmer Archipelago in Antarctica. The orange line running through the data is the SVM's chosen decision boundary, and the surrounding yellow band represents that all-important margin we just mentioned. Notice carefully that the boundary doesn't simply touch the very nearest points of each species as closely as possible, deliberately, mathematically keeps a healthy, properly maximized buffer of safe distance from both groups simultaneously. Support vector machines can also use a clever mathematical trick called a kernel trick to draw fully curved non-straight boundaries for situations where a simple straight line clearly isn't enough to separate the two classes well. A decision tree works in a way that I suspect feels the most naturally, intuitively human of absolutely everything we have covered so far today. It simply asks one clear question at a time, much like a careful diagnostic checklist. The diagram here is a deliberately playful, slightly self-referential example. Deciding whether to use a decision tree at all by asking a small sequence of sensible questions like, do I need an easy explanation for this decision? And do I need to handle complex, non-linear patterns? Each answer you give creates a new branch in the tree, and you simply follow these branches downward, one decision at a time, until you eventually land on a final class or numerical value at the bottom. This particular structure is extremely easy to explain clearly to absolutely anyone, including a non-technical audience, or, importantly, a court of law if a decision is ever formally challenged. You can literally trace, out loud, the exact sequence of questions that led directly to any given final decision. The genuine catch is that trees, if left completely unconstrained during training, can grow extremely complex very quickly, with very deep, narrow branches that often exist purely to accommodate one or two unusual, possibly noisy training examples, rather than any genuine underlying pattern. That natural tendency toward excessive, unnecessary complexity is exactly why pruning exists as a standard, well-established technique in practice. Very deep, unpruned trees can effectively memorize their specific training data, rather than learning a general, transferable pattern, the same overfitting problem we discussed earlier, just appearing here in a new guise. Too many fine-grained branches actively hurt generalization performance on new cases the tree hasn't seen. Pruning deliberately removes some of these excess branches after the fact, simplifying the overall tree structure considerably and somewhat counterintuitively, at first glance, simpler. Noticeably, shallower tree frequently performs measurably better on new, unseen data than an enormous, sprawling, unpruned one, while also remaining considerably easier for a human reviewer to interpret, trust, and explain to others. A single decision tree, even one that has been carefully and properly pruned, can still be somewhat unstable in practice. Quite small changes in the underlying training data can sometimes produce a noticeably different resulting tree structure entirely. Random forests solve this particular instability problem by deliberately building many separate decision trees, each one trained on a slightly different randomly resampled portion of the original training data, exactly as shown in the diagram. Critically, each individual tree in the forest is also typically restricted to considering only a random subset of the available features at each branching point, which further decorrelates the different trees from one another and makes the overall forest considerably more robust than it would otherwise be. Each tree then produces its own individual prediction, and all of those separate predictions are finally combined or aggregated together. Essentially, the whole forest of trees votes collectively to reach one single, noticeably more stable final prediction. This dramatically improves both stability and overall accuracy compared to relying on any single tree alone, though, as a direct and unavoidable trade-off. The resulting forest is noticeably less transparent and considerably harder to fully explain to a non-technical audience than any single tree on its own would be. Boosted trees take an entirely different strategy for combining multiple individual trees together, building them not all at once in parallel the way a random forest does, but rather one after another, in careful, deliberate sequence. Each new tree added to the sequence is specifically, deliberately built to focus its limited attention on correcting the particular mistakes made by all the trees that came immediately before it in the sequence. Through this patient, sequential, error-correcting process, many individually weak learners, trees that on their own are only marginally better than simple random guessing, gradually combine together into a single, often remarkably strong and highly accurate overall model. The genuine trade-off here is that boosted trees typically need considerably more careful, hands-on tuning of their various internal settings than a comparatively straightforward random forest does, in order to reliably get the best possible results out of them. Neural networks bring us, in a satisfying way, full circle back to the connectedness tradition we covered in considerable historical detail earlier today. McCulloch and Pitts's mathematical neuron, Hebb's learning rule, and Rosenblatt's original perceptron. Input data passes through one or more layers of these simple, neuron-inspired computational units, stacked one after another. The connections between these units carry adjustable weights, exactly like the perceptron's original weights, and the training process adjusts those weights systematically to reduce prediction errors, exactly as we carefully described several slides earlier today. Neural networks are particularly useful, in practice, for learning complex, non-obvious patterns that simpler algorithms, like plain linear regression, would struggle to capture at all. It's worth knowing that this entire connectedness tradition received its own remarkable, very recent vindication. In 2024, the Nobel Prize in Physics was jointly awarded to John Hopfield and Geoffrey Hinton, specifically for their foundational 1980s work on the mathematics underlying artificial neural networks, a striking, very public recognition more than 4 decades later that this entire connectedness approach, once nearly abandoned during the AI winter we discussed earlier, turned out to be deeply important after all. Deep learning is simply what you get when you deliberately stack a very large number of these neural network layers, one after another, very deep indeed, sometimes hundreds of layers in modern systems. And something remarkable happens when you do this at scale. The earliest layers closest to the raw input data automatically learn to detect very simple, low-level patterns, a basic edge, or a single patch of color, say, in an image being processed. Middle layers then automatically combine those simple detected patterns into noticeably more complex shapes and textures. Later layers, deeper still in the stack, combine those shapes into fully recognizable, complex objects, a face, a vehicle, or a particular tree species you're trying to identify from a photograph. Crucially, and this is remarkable when you stop to think about it, No human engineer anywhere manually designed any single one of these intermediate features by hand. The network discovered this entire hierarchy of representations entirely on its own, purely from exposure to data, provided it has access to enough of that data and enough raw computing power to train on properly. Let's pull everything from this whole algorithm tour together visually in one consolidated overview. Regression fits a line through the data. KNN simply checks nearby neighbors and lets them vote. SVM draws a single boundary, deliberately maximizing its margin on both sides. Trees ask a careful sequence of yes or no questions one at a time. Forests combine the independent votes of many separate trees together. Neural networks learn a deep hierarchy of increasingly abstract layers. All 6 of these methods, without exception, are what we technically call supervised methods. Every single one of them absolutely needs labeled examples, correct answers supplied in advance, in order to learn anything useful at all. But I want to deliberately add one more, different idea before we move on from this slide, because the image you can see on screen right now is illustrating it directly and quite beautifully. Clustering. Look at that picture carefully. A jumbled pile of completely unlabeled objects on the left, automatically sorting themselves into sensible, coherent groups on the right, dogs together, vehicles together, items of furniture together. Bags together, pieces of fruit together, with absolutely no human anywhere telling the underlying algorithm in advance what those specific groups should be, or even how many distinct groups to expect at the outset. That is an entirely different family of algorithm altogether, needing no labels whatsoever to function, and it provides the perfect natural bridge straight into our very next topic. Before we move fully into that next topic though, one crucial, genuinely humbling principle, formally proven within machine learning theory, and properly known as the no free lunch theorem. No single algorithm, however clever or fashionable, wins on every possible problem you could throw at it, universally and without exception. A simple model can sometimes comfortably beat a far more complex, more fashionable one, depending entirely on the specific characteristics of your data and your specific underlying goal. Raw predictive accuracy is never the only thing that matters in practice. Explainability frequently matters just as much, sometimes considerably more, especially in any official, administrative, or legal context where decisions need to be justified afterward. And rigorous, honest testing, carried out properly on data the model has never seen during training, is the only reliable way to discover which particular algorithm actually works best for your specific problem at hand. There is, frustratingly but importantly, no clever theoretical shortcut around that necessary empirical testing step, no matter how experienced you eventually become. Let's now organize this entire algorithm landscape we've just toured using a more fundamental, more important underlying dimension. How much supervision, in the specific form of labels, a given method actually requires from a human in order to learn anything at all. Supervised learning, which accurately describes every single algorithm we just toured together in detail, learns from labeled data specifically, meaning every single training example comes already attached to a known, correct answer supplied in advance. It is used both for classification, predicting discrete categories, and for regression, predicting continuous numbers. It does require human labeled data, which can be quite expensive and time-consuming to produce properly at any real scale, but it nonetheless remains, by a wide margin, the most common and best uttered form of practical machine learning in active everyday use today across nearly every industry. Unsupervised learning, by sharp and deliberate contrast, works with absolutely no labeled answers at all, exactly the clustering example we deliberately previewed a couple of slides ago on the algorithm comparison slide. It finds meaningful groups or recurring patterns hiding directly within the raw data itself, with no outside guidance. It proves especially useful for open-ended exploration, precisely when you don't actually know in advance what categories or underlying structures you should even be looking for. It can reveal hidden structure in your data that literally nobody on the team had anticipated beforehand. The diagram currently on screen shows the 2 major families within this broader approach. Clustering techniques, like the well-known K-means algorithm, which groups similar items together based purely on their measured similarity, and dimensionality reduction techniques, like principal component analysis, commonly abbreviated PCA, which simplify complex, high-dimensional data down into something a human analyst can actually visualize and meaningfully interpret on a simple 2-dimensional chart. The genuine catch is that properly interpreting exactly what an unsupervised model has actually found after the fact still typically requires careful, informed human judgment to make sense of it. Semi-supervised learning sits deliberately, usefully between these two extremes we've just discussed. You have only a relatively small number of carefully labeled examples available, but a much larger surrounding pool of entirely unlabeled examples that costs nothing extra to collect. The model cleverly leverages both sources of information together, which substantially reduces the overall cost and effort of labeling everything by hand, while still benefiting from the rich underlying structure present in that much larger unlabeled pool of data. This particular approach proves especially valuable whenever careful labeling is expensive or time-consuming to produce reliably. Think, for instance, of a trained ecologist's scarce professional time being specifically needed to correctly label rare or visually ambiguous species occurrences in a large photo archive. Reinforcement learning works through an entirely different underlying mechanism altogether, one that should feel quite familiar by now given our earlier discussion this morning of learning directly from lived experience. An agent, which might be a piece of software or a physical robot, takes some specific action within its environment. The surrounding environment then responds in some way to that particular action. Rewards and penalties, arising naturally from that environmental response, then guide and shape all further learning going forward. Over many repeated interactions with the environment, the agent gradually learns an effective overall strategy for behaving successfully within it. This particular approach is widely used in competitive game-playing systems and in physical robotics specifically, precisely in situations where there isn't already a pre-existing dataset of correct labeled answers sitting around waiting to be used. The agent has to learn everything through its own direct, often initially quite clumsy and inefficient, trial and error. Self-supervised learning is a clever and increasingly important approach in modern AI here. The model starts with unlabeled data, for example, many images, documents, audio clips, or large amounts of text, without anyone manually writing labels for every example. Instead, the system creates its own learning task from the data itself. For example, in an image, we may hide a patch and train the model to predict the missing part, or we may show two different views of the same image and train the model to recognize that they belong together. In text, a similar idea is used when a word or token is hidden or predicted from the surrounding context. The key point is that the raw data itself provides the training signal. No human has to separately label each example for that task. Through this process, the model learns useful internal representations, patterns, features, and relationships, which can later be fine-tuned for downstream tasks, such as classifying an image as a dog. This is why self-supervised learning is so important. It greatly reduces dependence on expensive labeled datasets and forms the foundation of how many modern AI systems, including large language models, are pre-trained at massive scale. Transfer learning offers a practical shortcut that neatly sidesteps a great deal of the labeling cost and computing expense we've been discussing throughout this section. Rather than training an entirely new model completely from scratch every single time, you instead start with a model that has already been carefully pre-trained on some large, fairly general task. And then you simply adapt that existing model to your own, considerably more specific task of interest. This typically needs substantially less of your own carefully labeled data, and it saves enormous amounts of both time and raw computational cost compared to starting over. It is now extremely widely used throughout applied deep learning, for instance, adapting a general-purpose pre-trained image recognition model, originally trained on millions of generic internet photographs, to specifically recognize particular wildlife species from your own camera-trap photographs, rather than laboriously training a brand new model entirely from zero using only your own limited, hard-won field data. We are now ready to discuss the technology behind much of the recent excitement around artificial intelligence, large language models. A large language model is trained on enormous collections of text, books, websites, articles, documents, code, and other written material. During training, it does not memorize everything like a library catalog. Instead, it learns patterns in language, which words, phrases, ideas, and structures tend to follow one another in different contexts. At a simplified level, when we give it a prompt, it generates the next likely pieces of text, one after another, based on those learned patterns. This is why it can produce fluent, coherent, and very natural-sounding answers. It can summarize long material, draft letters, explain concepts, rewrite text, and help us think through a problem. But this point is extremely important. A large language model is not the same as a factual database. It does not simply open a record, look up the correct answer, and reproduce it. It generates an answer. Most of the time that answer may be useful, but because it is generated rather than directly retrieved, it can also be incomplete, outdated, or confidently wrong. So the key idea to remember is this. LLMs are very powerful language generators, but they still need human judgment, verification, and proper use. To properly understand how these large models actually process human language internally, you need two closely related key concepts, tokens and the context window. Raw text is first broken down mechanically into smaller chunks called tokens before the model can process any of it at all. These are not necessarily whole, complete words. They are often smaller, partial word pieces, especially for longer or less common words. The model can only directly see and actively process a strictly limited number of these tokens at any one time. That limited span is formally called its context window. Sufficiently long documents can overflow this window entirely, meaning earlier details, mentioned much earlier in a long conversation or document, might simply be missed, dropped, or effectively forgotten by the model entirely. It's important to understand clearly that this context window is fundamentally not the same thing at all as ordinary human memory, once something has fallen entirely outside that window. The model generally has no other persistent, reliable way of recalling it later, unlike a person who might still vaguely remember something from much earlier. Embeddings provide the deeper, somewhat more technical underlying mechanism that makes much of this sophisticated language processing actually work in practice. The basic underlying idea is to convert ordinary text into purely numerical vectors, essentially just long, ordered lists of numbers, positioned carefully within a high-dimensional mathematical space. Constructed specifically so that pieces of text with similar meanings end up positioned close together in that abstract space, while completely unrelated pieces of text end up positioned much farther apart from each other. This particular numerical representation of meaning is precisely what powers modern semantic search and retrieval systems, letting a system reliably find conceptually related documents, even when those documents don't happen to share many or even any of the exact same specific words. This particular concept also turns out to be a crucial building block for the very next topic we are about to cover together. That next topic is RAG, short for Retrieval Augmented Generation, and the diagram currently on screen walks through the whole process clearly, one step at a time. The system first searches systematically across a curated collection of relevant documents, using exactly the embeddings concept we just carefully introduced a moment ago. It retrieves whichever specific passages it judges to be most relevant to the current query. It then brings that freshly retrieved context directly into the prompt eventually given to the underlying language model. And the model finally generates a complete answer that is grounded in that specific retrieved supporting material, rather than relying purely on whatever it happened to memorize, possibly imperfectly, during its original, much earlier training process. This particular technique significantly reduces, though it does not, importantly, entirely eliminate, the genuine risk of hallucination. The fabrication problem we are about to discuss in considerably more detail shortly. Careful verification by a knowledgeable human reviewer remains absolutely essential regardless, even when RAG is being used properly. AI agents represent a further, considerably more ambitious step beyond simple, single-turn question answering, of the kind we've discussed so far. The diagram on screen shows the typical recurring workflow involved. An agent can carefully plan out a sequence of distinct steps required to accomplish some specified goal. Actively use external tools along the way as needed. Call other pieces of software, our external APIs, directly when required, and act with a meaningful degree of autonomy, without necessarily requiring a human reviewer to explicitly approve literally every single intermediate step along the way. This capability is genuinely powerful, opening up real practical applications, but it also needs strong, deliberately engineered safeguards built in from the start, precisely because an agent acting with real, unsupervised autonomy can take real-world, potentially quite consequential actions based on nothing more than a single piece of flawed or subtly mistaken reasoning that nobody happened to catch in time. Let's pause here for a moment and ask an important, slightly uncomfortable question. Why does AI so often feel so convincingly, almost eerily intelligent to us as users, even when, as we are about to see quite concretely, it can simultaneously be deeply, confidently, and completely wrong about basic facts? It uses remarkably fluent, natural-sounding language that reads just like a confident human expert would write. It combines information drawn from many different sources very quickly, far faster than any human researcher possibly could. It adapts smoothly and convincingly to almost any way you happen to phrase your particular question or prompt. It can handle many wildly different formats and tasks competently, switching between them instantly. But, and this is genuinely the single most important sentence in this entire section of today's session, so please do remember it clearly, fluency is simply not the same thing as reliability, no matter how convincing the fluency feels in the moment. A confident, perfectly grammatical, beautifully structured sentence carries absolutely no built-in guarantee whatsoever of actually being true. This brings us directly to hallucination, one of the most important practical risks for every one of you to understand clearly and to actively guard against in your own future official work. A model can produce output that sounds entirely confident and authoritative on the surface, while simultaneously being factually incorrect underneath that confident surface. It may straightforwardly invent facts outright or even entirely fabricate citations and supporting sources that simply do not exist anywhere in reality, complete with plausible-looking author names and publication years. This fabricated output frequently sounds extremely polished, well-organized, and authoritative in tone. There is usually no obvious stylistic warning sign whatsoever that something has gone quietly wrong underneath. This becomes far more dangerous specifically in official government work of the kind many of you will be doing, where a single fabricated fact, if it goes unchecked by a careless reviewer, can flow directly into a formal report, a sworn affidavit, or an actual policy decision with real consequences for real people. The rule here, without any exception whatsoever, is simple. Always verify any genuinely important claim independently, through a separate and reliable source, before relying on it in any official capacity. Bias and data quality represent a closely related but distinct risk, one we already previewed briefly earlier today when discussing how ordinary heuristics can quietly turn into bias over time. Models learn directly and entirely from past, historical data, and bad, unrepresentative or systematically skewed data inevitably produces bad, systematically skewed outputs, with no exceptions. The diagram currently on screen shows this entire pipeline quite clearly. Messy, incomplete, or quietly biased input data flows straight through the trained model and directly into visibly biased outputs, such as the unfairly elevated risk scores shown here for several individuals. Entire groups of people can be effectively ignored or systematically underrepresented in a model's outputs if they happen to be poorly represented in the original training data to begin with. And because automation, by its very nature, operates at genuine scale across thousands or millions of cases, any bias present in a model doesn't just quietly persist in the background, it actively, mechanically scales up, potentially affecting a great many individual decisions very rapidly and simultaneously. This is precisely why rigorous systematic data auditing is an absolutely essential, non-optional step in any serious deployment, not some kind of optional extra nicety to be skipped under time pressure. Black box behavior and explainability bring us back, in a satisfying sense, to the original symbolic versus connectionist trade-off we carefully discussed earlier in today's historical section. Some of today's most powerful, most capable models are opaque internally. Even their own original creators cannot always fully explain precisely why the model produced one specific prediction rather than some other, equally plausible sounding alternative. A given prediction can arrive with absolutely no accompanying reasons attached to it at all, just a bare output. This inherent opacity makes such predictions difficult to meaningfully challenge or properly contest after the fact, whether in an internal review or a formal legal proceeding. Explainability matters enormously in any governance or administrative context specifically, where decisions frequently need to be properly justified and carefully defended afterward, often directly to a court, a tribunal, or an aggrieved citizen demanding a clear answer. And ultimately, human reasoning and considered human judgment remain absolutely necessary, precisely because of this persistent gap, a model's opaque, unexplained output, however confident sounding it happens to be on the surface, simply cannot substitute for accountable human review by someone who can be questioned directly. Let's close this risk discussion by being balanced, looking at real, well-documented successes, alongside equally well-documented warnings. The diagram lays both columns out side by side. On the success side, DeepMind's AlphaFold cracked a 50-year-old open problem in biology by accurately predicting protein structure directly from amino acid sequences. Work significant enough to earn Demis Hassabis and John Jumper a shared half of the 2024 Nobel Prize in Chemistry, with the other half going to David Baker for related work on designing new proteins. By the time of that announcement, AlphaFold's freely released predictions had already been used by over 2 million researchers across roughly 190 countries, covering more than 200 million proteins, work that previously could take a single laboratory years to accomplish for just one protein. AI-powered translation tools have also meaningfully improved accessibility across language barriers worldwide. Now the caution's equally real. In early 2023, Google's Bard chatbot, in its own promotional video, confidently misstated a basic fact about the James Webb Space Telescope. And that single public error contributed to Alphabet's shares dropping roughly 8% in a day, wiping out something in the region of $100 billion in market value before lunchtime. Separately, in the widely reported Mata versus Avianca case, a lawyer named Stephen Schwartz submitted a U.S. federal court brief confidently citing several entirely fabricated cases generated by ChatGPT, complete with invented names like Varghese versus China Southern Airlines. The presiding judge fined the attorneys $5,000 and ordered them to personally notify every judge falsely named as the author of a fabricated opinion. And in a Canadian case, Air Canada was held liable by a tribunal after its own website chatbot wrongly told a grieving passenger he could claim a bereavement fare retroactively. When the airline argued the chatbot was a separate legal entity, the tribunal flatly rejected that and ordered it to pay regardless. Autonomous systems more broadly carry real, ongoing safety risks that responsible deployment must take seriously. The lesson from both columns together is not avoid AI, it's use it with your eyes open and verify before you rely. Let's close, then, with the single most important takeaway I want every one of you to carry out of this room with you today, more than any individual historical fact or algorithm name. AI assists humans decide that particular ordering of the two words is entirely deliberate, and the two roles are absolutely not interchangeable, however convenient it might sometimes feel to blur them. Models predict, officers like yourselves verify, especially and specifically before any official action is ever taken on the strength of that prediction alone. Data and context always matter enormously in practice, and a model's output is frequently only as good, and only as trustworthy, as the data it happened to be trained on, data whose origins and limitations the end user may well have no visibility into at all. Errors made by automated systems can scale up and propagate very rapidly, indeed far faster and far wider than any single human's individual honest mistake ever realistically could on its own. And accountability, in the end, remains entirely and irreducibly human. With no way around it, a model cannot be formally held responsible for an outcome, cannot testify under oath, and cannot be meaningfully cross-examined about its reasoning, but you certainly can, and quite possibly will be, for any decision ultimately made in your name and under your signature. So, use AI, period. Use it well, and use it often, once you see where it helps you do your job better. But never, under any circumstances, surrender your own considered judgment to it. With that, let's take a short break before we move into this afternoon's hands-on demonstration.